Hello everyone, welcome to my contribution to the 28th International Workshop on Weak Interactions and Neutrinos. I'm Robert Ward. I'm talking on behalf of the UC collaboration about our search for light dark matter with spherical proportional counters. So I'll give a quick overview first about the evidence for dark matter and why we're looking for it in the first place. So evidence suggests that 85% of the matter content of the universe is comprised of this invisible component that we can't see. So there's significant evidence for this from astrophysical observations, and there's a collection here at the top. I won't be able to go through each of these, but if you're interested, there's some papers here. So you have rotation curves of spiral galaxies, bullet cluster vision, and then dark filaments in large-scale structure formation. The important point is that nothing in the standard model, although we have all this astrophysical evidence, gravitational evidence of this, nothing in the standard model can account for this on the particle level. So there are many theories proposed to explain the nature of dark matter. We have a paper here summarizing all the different theories and how the different different detectors are looking at trying to find them. But the preferred candidate is called the WIMP, so the weakly interacting massive particle. But there's an absence of conclusive evidence in the preferred mass range of the WIMP, so from 10 GeV to 1 TeV. So this plot here shows the experimental constraints on the different cross sections for the WIMP nucleon cross section versus WIMP mass. So there's much weaker constraints in the 0.1 to 10 GeV mass range. So this is a good motivation. Given the lack of conclusive evidence in the preferred mass range and the weak constraints, this is a good motivation to search in these lighter WIMP mass regions. And this is where the UC collaboration comes in, try and explore this circle. So we have some initial constraints here from a prototype experiment, and we want to move further down into this region. So the UC collaboration stands for New Experiments with Spheres Gas. We're a collaboration of 5 countries and 10 institutes with about 40 collaborators. So this image here is the Zoom meeting from December, so the collaboration meeting December 2020. We have 3 deep underground laboratories helping us conduct these experiments. So we have Snow Lab in Canada, the LSM in France, and then Booby Mine in the United Kingdom. So the way we actually plan on detecting these low mass dark matter particles is through nuclear recoil. This gives a good handle to see these light dark matter candidates. So what happens is your dark matter candidate comes in, hits your nucleus, and then deposits the recoil energy about on the order of keV. Here's what the recoil energy distribution looks like. So you have the recoil energy on the bottom, and then the likelihood of that interaction on the top for different target gases, and WIMP mass of 1 GeV, dark matter mass of 1 GeV. The important thing to note is that the closer in mass that this dark matter candidate is to the nucleus, the more recoil energy is deposited. So to detect this nuclear recoil, you require low detection thresholds, so on the order of keV, low mass targets, and then a favorable quenching factor, where the quenching factor is a portion of recoil energy converted to the detectable signal. And the important point is that it's more favorable, the lighter your target, the more favorable your quenching factor is. And here's a plot up here of a bunch of different target nuclei and different target gases showing this. So the spherical proportional counter is the detector we're using. So why is it good for actually detecting nuclear recoil then? So spherical proportional counter is a spherical cathode shell which holds gas volume, and at the middle we have the anode, which is held in place by a grounded rod. High voltage is supplied to the anode, and this sets up the electric field in your detector, which, as it's a sphere, varies as 1 over r squared. This 1 over r squared dependence divides your detector into a drift region and the avalanche region, where your initial interaction occurs in the drift region. Your primary electrons will drift toward the avalanche region, where about 1 millimeter from the anode, they gain enough energy from the high electric field to cause further ionization. This causes an avalanche, and then this is a nuisance response in your detector, which you detect. So the benefit of the spherical shape as well is that it has a capacitance independence of the detector size, and it gives you very low electronic noise, which is low enough that you can even detect this potential to detect singular electron events. So very light thresholds, very small thresholds. So the benefit about the spherical shape is that it's a maximum volume to surface ratio. Most of your backgrounds come from the surface, so you want to have as much volume as possible. High pressure operation, higher the pressure, the more gas you fit in, more target mass for appropriate case. And the other thing is that it's a simple, robust design, and you have a flexibility in target gas to optimize which, what mass of dark matter candidate you're looking at. This picture here then is of the original detector, going over a decade ago now. And this is made of an old lead cavity. Yeah, it was a repurposed radio frequency lead cavity. So I've explained a bit of how you get the detector response. How can we just discern the different types of interactions in your detector? And you do this with pulse shape analysis. So on the x-axis we have the amplitude of the event, and on the y-axis we have the rise time. We've got three different event types here. You have first, we have muon-like events. So muon will go through your detector. It will deposit. It'll go through as a track, deposit a whole line of pyroionization, and then these electrons will drift to your anode over a very wide spread of times. So this leads to high rise time events, where just to say the rise time in an event is usually defined as the time it takes for the pulse to get from 10% of its amplitude to 90% of its amplitude. And as there's such a wide variation in possible tracks for your muon, you have a wide range in amplitudes as well. The second one then is the surface-like events. So these are where your backgrounds are going to come from the edge of your detector. These are all point-like events, so they all happen in a very small space. But because they're at the edge of the detector, they're at a high radius, the spread, the electrons have a long time to diffuse, so they will arrive at a big spread of times, which leads to a high radius, a high rise time event. Signal-like events then, these will be a specific amplitude because it's a specific energy deposition. So for instance, here we have 5.9 keV X-rays from the decay of iron 55. And the idea with signal events is that they can occur anywhere in the detector volume. So you can have very low rise times if the event happens close to the anode, because the electrons have a small time to diffuse. And then if the event goes further out of the detector, you can also get the high rise times as well. But the idea is then, if you want, you can reject your backgrounds using a rise time cut, for instance, to get rid of events happening at the surface and muon-like events. This is good for signal discrimination. So then, I'll talk now about the prototype detector, SEDIN. So this is a 60 centimeter diameter spherical proportional counter based at the LSM in France. It was made of ultra pure NOSV copper and chemically cleaned several times to remove radon deposits to reduce the background as much as we could. The LSM is placed at 4,800 meters water equivalent in underground in France on the French-Italian border. And this is what the shielding looked like as well. So the SEDIN detector is this copper cathode here. This is placed in 30 centimeter polyethylene shielding, 15 centimeters of lead cube, and then 8 centimeters of copper as well as the detector itself. So the anode used in this was 6.3 millimeters silicon anode. So here is what the results from this prototype were. We used a gas mixture of neon CH4, 99.3% neon, 3.1 bar to give us a 282 gram target mass. This detector was running for 34.1 live days, which gives us a 9.6 kilogram day exposure. And here's at the time, this is what the cross sections are excluded. So in this region up here, we have competitive results. So we were the first people to set constraints on 0.5 GeV dark matter particles at 4.4 times 10 to the minus 37 centimeters squared, 9% confidence limit. And this is for spin independent whips. So this is a good competitive first result. How do we improve for the next stages? So if we want to go further down in cross section, we reduce our backgrounds and increase our exposure. If you want to go further to the left, so look at a lower wave mass, we can reduce our energy thresholds further and increase, reduce our target nucleus mass. So for instance, look at helium, hydrogen, things like that. So then, the next detector, the current generation is called Snow Globe. This is a 140 centimeter spherical proportional counter based at the Snow Lab in Canada, so the Sudbury Neutrino Observatory. So this was constructed and tested at LSM and then transported over there. So already you can see one of the benefits of Snow Lab is that's a lot further deeper underground. So you have a smaller muon flux, for instance. The other thing is that we use an improved multi-anode Achenos sensor. I'll talk about that in a little bit more detail. We have also made it out of 4N copper, so this is 99.99% pure copper. And to reduce backgrounds further beyond this pure copper, we've electroplated the interior surface for further background suppression. So this is a picture of the detector being spun. I'll talk about electroplating in a second. This is a picture of the detector being spun, and this is what it looked like when it was still in the LSM. So the Achenos, so just to say, there are some issues with the single anode sensor in that the drift and amplification fields are connected. If you want to increase the field in your drift region, then you need to increase the voltage on your anode to the point where it starts sparking, or alternatively you need to increase the anode radius, which then leads to lower gains. So the Achenos comes in to try and solve these issues, and what it is a multiple anode sensor where you have multiple anodes and equal radii from the center of your ball, and this decouples the drift and amplification fields. So the amplification is determined by the individual anode, but the electric field in the drift region is determined by the collection of all of these anodes together. So we have a plot here of radius versus electric field strength, and the single anode has very low electric field in the drift region, but as you increase the number of anodes, you can increase this electric field in the drift region. The reason why you want to do this is that low fields in the region causes things like recombination attachment. So using the Achenos, you have several new capabilities. You can use large volume detectors operating at higher gas pressures, so this increases your target mass as much as possible. And it allows you to use smaller radius anodes below the level of 1 millimeter, for instance, and this can increase your gain and get you a much better signal to noise ratio. And the other opportunity is multiple channel individual anode readout, and this is useful for instance, getting position information of the event in your detector. So just to see, the Achenos, the reason why it's called Achenos is because this is the Greek name for sea urchin, and you can see the resemblance between the sensor and those creatures here. And if you're interested, there are some papers on Achenos development as well. The links are there. So I mentioned multiple channel readout and how this is used for position information of your event in your detector. So there's a lot of R&D underway at the moment on how to do this, and this is using the Birmingham simulation framework. So this is something I was involved a lot in, and this framework that can simulate spherical proportional counters combining the strengths of Janforth and Garfield ++. If you're interested, there's a paper here where I've described how this works. But for the first tests of multiple channel readout, we took the Achenos and split into two channels. You have the near electrodes, so the anodes near to the rod, and the far electrodes on the other side, so the ones away from the rod. So by splitting it into near and far, you get a sense of the zenith angle of your event by looking at the asymmetry of the pulse amplitude. So if most of your pulse amplitude is on your near electrodes, then the event must have happened near the rod. Whereas if most of your amplitude is on the far electrodes, it must have evented on the bottom part of the detector. That's how you get a sense of the zenith angle with the two channel, and get a sense of the pulse rise time. The pulse rise time gives you a sense of the radius of the event. So this is what I was talking about earlier with the pulse discrimination as well. So the closer the event happened to the anode, the smaller the rise time. So if you have high rise time events, this can give you a sense of where the event occurred. So using this, then you have a sense of the zenith angle and as well as the radius, even with just two channels. Moving further down the line, there's a lot of R&D looking at how we can use individual anode readout. So have every single anode attached to a separate channel. It's the key area of simulation development. And we have an example here of the 60 anode Achenos, where each one of those is individually wired up. So you can see the signal on each one of those anodes. And this gives you the potential for track reconstruction. So here's an example of a muon going through the detector. The muon will leave a track of ionization, and those electrons will be deposited on the anodes nearest, where it happened. This can tell you a bit of how the muon must have passed through your detector. And this is helpful in things like background rejection, etc. So the other thing then is that if you know which anode that the event occurred on, then you get a sense of direction of where the dark matter came from, or where the event came from in your detector. And there are some dark matter theories, like dark matter winds, where there is a direction to the dark matter. So this gives you some sensitivity to those theories as well. So this is a key area of simulation development for down the line. Moving on then, there are a lot of background events to consider with these detectors. So copper is used for the cathode because copper itself is strong, it's pure, it's inexpensive, and there's no long-lived radioisotopes. So that means that copper itself will not give much background to your detector. However, there are some things to consider with regards to impurities and cosmogenic activation of your copper shell. So there are some background sources. So first is cobalt-60 can be produced from copper by fast neutrons from cosmic muon spallation. And then secondly, you have impurities from the uranium-238 decay chain. And this can be added to by radon gas, which is found naturally in the atmosphere. So radon gas can deposit parts of the uranium-238 decay chain during manufacturing. So the issue with uranium-238 decay chain is that it has this isotope called lead-210. This is a very long-lived isotope on the order of 22 years half-life. And this can be an important background for your, this can be an important background in your experiment. So the way we infer the lead-210 activity of the 4N copper used to produce a snow lab is by measuring the 210 polonium activity. There's a plot of this here, and the estimate is that we have a contamination of, well, the radioactivity of lead-210 in our NuSG detector is 28 plus or minus 80 millibecquerels per kilogram. And here's the paper as well. So the way to reduce the effect of this background is by using a technique called electroplating. This is a way to transport ions from an inner hemisphere. So in this example, you transport ions from an inner hemisphere of copper to the inner surface of the snow globe detector by setting up an electric field. And using this technique, we applied 500 micrometers of extremely pure internal shield to the snow globe. And this was found to reduce the background rate from, for instance, the impurities below 1 kV by 70%. So this is a very, very extremely pure shield. The exciting thing here is that the growth rate achieved was about 1 millimeter per month, which gives the potential for fully electroformed detectors, and I'll talk about that later. But yes, this was the first large-scale deep underground radiopolar electroformation. You have a plot here of the how much was deposited, depending on the time. So the snow globe then, this is the physics potential. Using a gas mixture of neon CH4, and the plan is to have 20 kilogram day exposure. And this is how it improves on Sedene. So this is the snow globe estimated sensitivity, and the data taken has started. But how can we improve from snow globe? So I mentioned, so that the main backgrounds to deal with in these experiments now is cosmogenic activation. So where muons come in and, for instance, form that cobalt-60. Backgrounds from impurity in the copper as well. So one way to tackle both of these at the same time is the ECUM experiment, so the electroformed cuprum manufacturing experiment, where cuprum is the Latin name for copper. And the plan is to completely electroform a detector at SNOLAB underground with this 1 millimeter per month growth rate. So the ECUM sphere is going to be 140 centimeter in diameter and will completely replace snow globe. And this extremely pure, because we have an extremely pure copper shell and minimal cosmogenic activation because it's built on the ground, we're going to get better sensitivity. So a 30 centimeter prototype is to be constructed this summer, with the full detector starting, the construction of the full detector starting late 2021. It's going to take about 8 months, I believe. Looking further down the line then, if we've tackled cosmogenic activation in copper, the next thing to look at is improving the shield. So that's one thing we're going to look at with the dark sphere experiment further down the line. And the other thing to do is just increase the target mass. So dark sphere is going to be a 3 meter diameter fully electroformed detector formed in Bulby Mine in the UK. Bulby isn't as low underground, as deep underground as NSM and SNOLAB, but it has the benefit of having a very low radon contamination. The proposed shielding is going to be a mixture of water and lead, and the plan is to have 27 kilograms of helium butane gas. And the other thing is that by this point, we want to have the 60 anode readout Achenos implemented as well, so we can get the full position information. So the construction for this is proposed for 2024. And this is how it's going to compare to the proposed the ECUM sensitivity as well. And the potential alongside nuclear recoils is to detect electron recoils as well. And this can all added together can help us reach the neutrino floor. So to summarize then, NuSG probes not very well constrained territory for light dark matter candidates on the range of 0.1 to 10 GeV using spherical proportional counters. We already have some first results out with the Sedene prototype in the NSM. The snow globe detector is the next generation detector and is now in operation at SNOLAB. And this has benefits of larger detector and target mass, lower backgrounds, and improved sensor. So looking further in the future, then we have the ECUM and dark sphere experiments using active R&D to help improve the Achenos sensor. You have electroform detectors and improve simulation. So the plan then is with ECUM being constructed later this year, dark sphere has the potential to reach the neutrino floor in 2025. So thank you very much for listening. This has been an overview of how the Neutrino experiment is searching for light dark matter candidates.